Hey, pre-calc students, this is going to be our third day of Unit 5, and it's essentially a practice day for us, but you'll notice that in the packet on page 9, it says Rational Functions Homeworks 2 and 3, so this is kind of counting as two different homeworks, and you're going to submit this to me on Google Classroom, and it's going to count as a 10-point homework. So because I'm feeling so nice, I'm going to help you get started on some of these questions, and then from there you should be able to finish the rest. Okay, so I'm going to wind up doing number 3 with you in this first page. And this first page is not graphing anything, it's just solving inequalities. So if you go back to the last lesson, we introduced the concept of solving rational inequalities. So there's two things that we have to partition around for something like number 3. We have to partition around the root, and we have to partition around the vertical asymptote. The root comes from that x int, whatever makes the top equal to 0, which is just x equals 0. There's no solving involved there. The vertical asymptote, of course, is whatever makes the bottom equal to 0, which is x equals 5. So as soon as you determine the two values to partition around, we come over to the number line. We put 0 and 5 here. And then just remember that we have to think about carefully, are these open circles, closed circles, a combination of one of each? And the reason why we might get a combo is, first of all, greater than or equal to 0 typically means closed circles. But it's only a closed circle where the root is. The vertical asymptote is always an open circle. So because of that, when I come over here, I'm going to put a closed circle where the root is, an open circle where that vertical asymptote at 5 is. And now I can clearly start partitioning and see where we're positive and negative. Oh, and by the way, what do we want? Greater than 0 means we want positive. Okay, so if I test -1, the top is, well, -1, which is negative. -1 minus 5 is negative, and negative over negative is positive. All right, moving on to x equals 1. The top would be positive. The bottom would be 1 minus 5, which is negative. Positive over negative is negative. And then if I test x equals 6, we're going to wind up getting positive over positive, which altogether is positive. And since we wanted positive, we can now shade to the left and shade to the right. Just being careful that when I now write my final solution to this question, and by the way, this is not enough just to say, okay, I've shaded, I'm done. You have to write the solution in interval notation, just like we've done in many other cases. It would be -infinity to 0 with a bracket, union 5 to infinity, and make sure you have 5 with parentheses there. Okay, so your job is to go back and do these two questions up here with rational inequalities, also number 4, which by the way is nicely factored for you to start anyway. But try those other 3 examples, and then you'll submit those at some point on Google Classroom to me. All right, if you look at the directions for the section on sketching, it says for each of the following rational functions, find all intercepts, asymptotes, and sketch the graph without using a graphing calculator. That's the whole point of this unit. And many of our units of study is to start thinking analytically about what do these graphs look like, what do we know about them, and how can we use some algebra to partition the graph and sketch it accurately. It also says to determine any kinds of symmetry here. Okay, so let's go ahead and actually, I'm going to have you try 1 and 2 on your own. So I'm going to leave those for you. Try number 1, try number 2. I'm going to jump over to number 3. This is one that I think will be good to do together, and then maybe I'll do one more in this packet. The rest will be for you to finish and submit on Classroom. All right, so going down and running down my list of key critical pieces of info, we definitely need the asymptotes. So there's a vertical asymptote at x equals 1. You don't have to show me setting this to 0 and adding the 1 over. You're going to get to a point where you can do that without showing me that step, and I'm okay with that. For horizontal asymptotes, keep in mind that we're looking for bottom heavy, equal heavy, or top heavy. This one happens to be equal heavy, right? Because the powers on the top and bottom are equal. So remember that you don't divide the exponents when it's equal heavy. You divide the coefficients of those leading equal heavy terms. So the coefficient of x to the first on the bottom is 1. It's a 3 on top. So 3 divided by 1 is 3. In a lot of instances, you will get y equals 1 sometimes if it's equal heavy, but students sometimes just too quickly default to that. Whereas in this case, y equals 3 is the horizontal asymptote. So be cautious about that. For x-intercepts, we're setting the numerator to 0. So when I do that, I get x equals 0. So the x-int coordinate-wise is 0, 0. I still want you to really focus on leaving vertical asymptotes as the equation x equals 1. x-intercepts, write it as a coordinate. This way you don't get confused and think that that's a vertical asymptote. Oh, and by the way, if the x-intercept is at the origin, the y-intercept should be there as well. Plug in 0 for x's on the top and bottom, you get 0 over -1, which is 0. So yep, 0, 0 is the y-intercept. So with all that information, putting it together over here, we need a vertical asymptote at x equals 1. We need a horizontal asymptote at, oops, I guess I need to, up here at y equals 3. And the only intercept we know is at 0, 0. We know it crosses the x and y axes right there. So when I do my partitioning, it's going to be a little tight here, right? Because we're partitioning around the x-axis specifically. We have an x-intercept at 0. We have a vertical asymptote at 1. So we're going to test values in each of these regions and kind of see what's going on. Okay, let's do the partitioning. If I test something like -1, 3 times -1 is negative. -1 minus 1 downstairs is negative. So that's altogether positive. In between 0 and 1, we got to be careful. Just test something like 0.5. 3 times 0.5 is a positive number. 0.5 minus 1 is negative. So altogether, that's negative. If I test 2, 3 times 2 is positive. And then 2 minus 1 on the bottom is positive. So we get positive over here. Okay. So how does this help me figure out what the sketch looks like then? Remember, positive means you're above the x-axis. You have positive y values there. Negative means you're below the x-axis. You got negative y values here. And then it switches back over to positive. Okay. So in this first section to the left of my x-int, can you imagine what the graph's going to look like if it has to be above the x-axis? I hope so. You're not going to go ahead and sketch something up here. There's no vertical asymptote to approach, right? We're not bound by the y-axis. Sometimes students incorrectly assume that. They're like, yeah, let me curve on up here, but the graph has no reason to want to hang out with the y-axis. There's no asymptote there. So being above the x-axis doesn't mean that it's going up forever. It just means that we have positive y values that are going to approach the horizontal asymptote at 3. Okay, so it's going to actually curve down, and of course it wants to hit that x-intercept. It's got to have to at some point. All right, and then what happens is the graph becomes negative. So now we're going to dip below the x-axis, and it won't be any surprise that we're going to head really close to that vertical asymptote. Finally, in the last region where we're positive, we're going to get a graph that's above the x-axis. And in this instance, the graph has no reason to hang out in here, because remember, there's no horizontal asymptote on the x-axis. We don't have to approach the x-axis. We have to approach the line y equals 3. And the closer I get to this vertical asymptote, if it's positive, we're going to head up forever. So you get this curve in this region. That, of course, kind of balances out this curve over here. We've seen graphs that look like this a lot in this rational functions unit. But when you're positive to the right of 1, you're going to get a curve bound by the asymptotes up in this region over here. Takes a little while to get used to, but try not to make the mistake of trying to like curve something in here. Okay, because remember, in the end, it has to be a function. Sometimes students draw this like sideways parabola that would fail the vertical line test, so that's no good. But also, the graph has no reason to hang out with the x-axis. No horizontal asymptote there, okay? So that's a complete look at the graph. If we're thinking about symmetry, the answer is that there is none to speak of. When we're talking about symmetry, it's mostly just y-axis and origin that I want you to answer, because sometimes those symmetries will be present. Okay, in that case, it's not. Okay. Last one I'm going to do is number 6, and then the rest you can try on your own. So for number 6, we got to find some vertical asymptotes, and because it's a little bit more complicated in the denominator, this one I will set to 0 and do the factoring here. So it's going to be x plus 3 and x minus 1. Okay, so just to make sure that we're on the right track there, we'll set that equal to 0 and factor. So we get x equals -3 and x equals 1 as the two vertical asymptotes. For the horizontal asymptote, we got to ask bottom heavy, equal heavy. Hopefully it's not top heavy. We don't know what to do with that yet. We just know it's not a horizontal asymptote, okay? But this one winds up being bottom heavy. X squared's heavier than the power on the top. So we get y equals 0 in that case for horizontal asymptotes. Okay. X int, set the top to 0. If x equals 0, well, then that's your x-intercept. Just like the last one I did with you, actually. So if the x-int is at 0, 0, no surprise that the y-int will be there as well. You plug in 0 for x here, here, and here. You get 0 divided by -3, which is 0. Okay, so we get our y-int in that same location. I'm going pretty quickly through that info, but once you get the hang of this sketching process, I promise that initial info we use to make our sketch should be pretty easy to find. Okay, so here are my two vertical asymptotes, -3 and +1. We've got 0, 0 as an intercept, and we know y equals 0 is our horizontal asymptote. So we've got a partition around the two vertical asymptotes at -3 and 1, and around the x-intercept at 0. Okay. Now I do think it's easier to partition in the factored form of the denominator. So if you want, you can replace this with x plus 3 times x minus 1. So when I start doing my testing, I'm not going to test in the original. I'm going to test in this factored form because that's what we determined it factors into. So if I test -4, top is negative. -4 plus 3 is negative. -4 minus 1 is negative. The bottom's technically positive right now, right? Negative times negative. Negative over positive is negative. And I'm going to start doing a quicker partitioning step too, because I'm hoping you guys are feeling pretty good about it. In between -3 and 0, like -1, top is negative. Bottom would be positive times negative. So the bottom's negative, the top is negative, so altogether this is positive. If I test 0.5, the top is positive, and then the bottom would be positive, negative. Bottom's negative, positive over negative is negative. And finally, to the right of 1, if I test 2, you're going to get positive, 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 which is positive altogether. How do I see what the graph looks like then? All right, if we're negative to the left of -3, we're going to be below the x-axis, bound by our asymptote. It's going to look like this. Then in this region, we switch over to positive. So now we're above the x-axis, and the closer I get to the vertical, it's going to head up to infinity, but eventually we got to come on down and hit that x-intercept at 0. And in between 0 and 1, this little tight window here, the graph does become negative. So now it's going to curve on through, approach the vertical asymptote at x equals 1, but headed down towards negative infinity. And finally, positive in the last region is going to be bound by the vertical asymptote, and it does want to get close to the x-axis because that's where the horizontal asymptote is. So in this last region, just like we had over here, we're going to get that kind of somewhat matching curve. I don't want to say it's exactly matching just because I don't want you to think this has origin symmetry. It's not quite there. Okay, these vertical asymptotes would have to have been equally spaced about the origin in order to be symmetric about the origin. So for symmetry for this one, we're going to say none again. But I'm sure there are other examples that you will find that have symmetry. Maybe this one up here. I'm not sure about it, but I'm thinking there will be some symmetry in other examples that you wind up sketching. Okay, so your job now is to go through and make sure that you can sketch the others. If you have any questions while you're working on it in class, you can let me know, but you'll submit this as 2 homework grades. So really make sure you do a nice job with your sketches, your accuracy, and go from there. Have a great rest of your day.